Yeah.
You do?
Before you leave today, hand in your homework or boxes. From your last one.
We're over?
No.
I thought you said all the chapters homework together.
Yeah, I thought we did that at the same time we did tests.
You can if you want, but
Doesn't it make it easier for you?
This is also mine. This is.
Oh, that's not your homework.
This is mine.
Oh, why was I taking it?
I don't know.
I don't know. It's just I can't give you feedback on it if you don't give it to me. But yeah, I will not accept homework after the test date. In other words, once we do a chapter 2 test, I don't want chapter 2 homework anymore. I don't care anymore. We're done with that material. We're moving on. I don't want you even spending time doing that homework anymore. So I don't accept homework after we do the chapter. After that, we're done. We're moving on to the next chapter. I'm done thinking about it, and I don't want you thinking about it. So there's no making up late homework past that point. Does that make sense?
Yeah.
The only way to make it up is doing the extra credit as we go through week by week.
Actually, which is very much right. Extra credit just counts as one extra problem, right?
It will be weighted out, so it gives you 5% bonus.
What if you
So
do like
take-
one extra credit problem here, one there?
It will be weighted out so that if you did all the extra credit throughout the year, you could have gotten an extra 5% on your homework and an extra 5% on your test.
So that means that for 20 weeks, you can make up one missed assignment.
For 20 weeks, you can make up one missed assignment? Not necessarily, no. That means that, so how much is homework worth on your grade? Did I say 50%?
I
30?
don't know.
Oh, yeah.
I think it's 50% of your grade. So that means if you average 90% on your homework and you do all the extra credit, you'll get 100% in that category.
Right, but I'm just saying that if you had missed a week of homework and test happened and you couldn't make it up anymore, it would take you 20 weeks to make up that assignment if you did the extra credit.
No, not necessarily, because not all homework has the same weight either.
Oh.
So on lighter homework, the extra credit is lighter. On heavier homework, the extra credit is heavier.
Okay.
But it gives you a 10% boost on your homework score, which is a 5% boost in the grade, because homework's 50% of your grade.
Okay.
So 10 extra credit problems. Well, that's not even necessarily true, but that gives you a sense for it.
Are you keeping track of the extra credit problems that we're doing?
Yeah, so far you have 0 credit on extra credit problems. Because I don't give, so maybe I should specify that. Homework I'm generous with your grade on, except for extra credit. Extra credit you gotta get right.
Right.
So an attempt at the extra credit doesn't count as any points.
So none of us have gotten any extra credit.
So no one has gotten an extra credit problem correct yet.
Okay.
Really?
Yes. Well, extra credit in my book should be harder to earn.
Well, yeah.
Because it's weighted so that an extra credit problem is worth a lot more than a single homework problem. Oops. Don't need that, don't need that. Everything's on the board. Alright, I think we're ready to go.
Do you have your camera on?
I thought I did, but no, I'm not positive. Yep, it's going. Thanks for the reminder. Okay, so today we're going to continue with set operations, which is everything I have on the board, and then after this we're going to do 2 examples of combinatorial proofs, counting proofs, and then that's it for today, then you'll be able to go to homework. So, should be a shorter day, and then obviously next week we have a test.
Yeah.
Right?
Yeah.
Okay. So, we've seen so far in this class operations on numbers, right? You take 2 numbers, you add them together, it gives you a number. You take 2 numbers, you multiply them together, it gives you a number. We've seen operations on booleans. If I take 2 statements and I OR them together, that gives me a statement. If I take 2 statements and I AND them together, that gives me a statement, right? You with me?
No, I'm going to space out. Sorry.
All right, zoned in. We're going to begin. Let's restart that conversation.
Okay.
So, you've seen operations on numbers. In other words, plus.
Yes.
I give you 2 numbers, you spit out a number. Multiply. Take 2 numbers, multiply them together, gives you a number. You've seen it with statements. You take two statements, you AND them together, it gives you a statement. A true statement and a false statement AND together gives you a false statement. Right?
Mm-hmm.
True or true equals true. You can use that a lot like you can use plus and multiply. Alright, so now we're going to do the same thing with sets. We're going to define operations on sets. You take two sets and you can union them together, which is going to be a lot like ORing together. And you can take two sets and you can intersect them, which is going to be a lot like ANDing statements. So we'll draw those parallels as we're going through, but it's an operation on sets. You give it two sets and it spits out a set. It's a binary operation. Take two sets as inputs, spits out a set as an output. So the two we're going to begin with are called union, and set intersection. The union of two sets, which we designate with this U, A union B is the way we read that, is equal to the set of all elements X where X is in A or X is in B. And this can be thought of as the logical OR, if you want, where X is in A is true or X is in B is true, right?
You never
Or they're
asked
both
for
true.
if there's any questions on homework.
We'll do questions on homework after I get through the whiteboard. So whatever. And then the intersection of two sets is the set of all X where X is in A and X is in B, and you can think about that as a logical AND. So let's see two examples of these, and then we'll re-go over these definitions to make sure they make sense. So let's say A equals the set 1, 2, 3, B equals the set, the set 3, 4, 5. A union B is the set of all elements where that element is in A or is in B. Is one in A or in B?
Yeah.
Oh, yeah.
So think about it. This is going to be kind of tedious. Your logic instantly says yes, but think about checking these two statements exactly. X, is one in A?
Yes.
Yes. Is one in B?
No.
No. Is one in A or in B?
Yes.
Yes. You see how X, or one's in A is true, one's in B is false, one's in A or one's in B is true. So it's in there together. So this is X such that whatever we put after is true, right? Might seem kind of tedious, but it's going to help you to start thinking about that way, this way. So 1 is in A or in B, so 1's in the union. 2's in A or B, so 2's in the union. 3's in A or B, so 3's in the union. 4's in A or B, so 4's in the union, and 5. Now let's look at the intersection. The intersection is a set of all elements where that element is in A and that element is in B. Right? Is 1 in A?
Yes.
Is 1 in B?
No.
Is 1 in A and 1 in B?
No.
So 1's not in the intersection. And the only element that's in A and in B is 3, so the intersection of the two is 3. So intuitively thinking, A union B is a set of all elements that's in A or in B. And A intersect B is a set of all elements that's in both A and B. Good? Alright. Common trick type questions to make sure you understand it. What's A union the empty set?
A, right?
Hang on. Whatever's in A and the empty set.
Well, A or the empty set, right?
No. It's all together.
That's not and.
So what goes here?
It'd just be A.
Just A?
No? Oh, sorry, 1, 2, 3.
Well,
Oh, ignoring these ones. Now we're saying for sets in general.
Okay, so it would be A and the empty set. Whatever's in A.
well, the empty set is already in
Okay, so this is correct. A union the empty set is A, but no, the empty set is not necessarily in A. The empty set is a subset of A.
A. Oh, that's what I meant.
Okay, but yes, so think about it. Take everything that's in A or the empty set. Well, nothing's in the empty set, so it's just everything in A,
Yeah.
right?
Yes.
So pretend that this was A for a second. Is 1 in A or in the empty set?
Uh-huh.
Is 2 in A or the empty set?
Right.
Is 3 in A or the empty set? So that's everything, because there's nothing in the empty set to check if it's an A. Okay, and then A intersect the empty set
Be the empty set.
would be the empty set. What's everything that's in here and in here?
Nothing.
Well, there's nothing in here.
So you can't have it.
Yeah, so nothing. Some pictures to help establish more intuition for what the empty set, or not the empty set, for what union and intersection give you, using some Venn diagrams. So this circle is a set of everything in A, and this circle is a set of everything in B. Everything I color green is what's in A union B, and everything in gray is what's in A intersection B. Might be pounding this home harder than I need to, but
It's important.
union and intersection are like the most basic math operations I could think of. I don't know what's more basic than those.
My life.
Your life is basic.
Yes.
I don't even know what that means. Okay,
Okay, that's good.
let's continue with some basic theorems about these operations. So you might remember that we proved that logic and an or are commutative and associative. That's exactly what we're saying here. A union B is equal to B union A. In other words, union is associative. And A intersect B is equal to B intersect A. Or in other words, intersection is associative. Commutative, sorry, this is commutative.
Yeah.
Down here is associative. A union B union C is equal to A union B union C. And then similarly with intersection, you can associate them however you want. And then finally, how do you distribute? How do you distribute union over intersection? And how do you distribute intersection over union? A union B intersect C is A union B intersect A union C. And A intersect B union C is equal to A intersect B union A intersect C. And this should look pretty familiar. For example, we proved that X or Y and Z is equal to X or Y and X or Z. And then similarly with that.
Oh, yeah.
And when you go to prove these things, you actually do it in terms of logic. So I'll give you an example proving one of these. And then you'll do the other ones on your homework, I think. I gave those to you. So let's see it in action, see how you use logic to do these things. And you'll see why I kept hammering thinking about this way home over and over again. So let's prove one of these. Let's prove associative. Let's prove that A union B union C is equal to A union B union C. So first off, use the definition directly. What's the definition of A union B? It's a set of all X where X is in that first thing or X is in that second thing. So this is a set of all X where X is in that first thing or X is in that second thing. You see how this is applying the definition directly? That's the biggest leap for these proofs. So make sure this makes sense, and I think after here it just kind of makes sense from there.
Just the definition.
Yeah, so going from here to here is just using the definition directly, right?
Right.
X is in that, or X is in that. Okay? Now we're going to apply the definition one more time for this. If X is in B union C, that means X is in B, or X is in C.
Hang on, what?
Are you good from here to here? Or is that where you stop?
Probably not.
Okay, so let's go back to the definition. We have set, union, set.
Okay.
That is equal to the set of all X such that X is in the first thing or X is in the second thing. We have set, union, set.
Okay.
That's the set of all X where X is in the first thing or X is in the second thing. Good so far?
Yeah.
Now we're going to use the definition internally on this. B union C, what's that?
B is in the first thing, or
X is in the first thing or X is in the second thing.
Oh, yeah.
So you see how we've now, once we got to here, all we have are statements and logical operators.
And it's all old.
We have a statement, we could have called that statement X, we could have called that statement Y, we could have called that statement Z. And viewed this as X or Y or Z, right? And so now we can just use what we already know about logic. We already know that logic is associative, so instead of associating these two statements together, I can associate these two statements together. And then reverse the definitions. Reverse the definition of that to there, and then this is the exact definition of that.
Okay.
So you're going to prove these in terms of logic using these definitions. It's going to feel really weird the first couple of these you do. I still remember the first couple of these I did. And it just felt so awkward. And I don't remember why, because now it's weird. So I remember that I had holdups when I was going through this. I just don't remember what they were. So what are your holdups if you have any?
I'm thinking about the third step right now.
Are you saying the step from here to here?
Yeah, I'm just trying to make sure I get it.
Yeah, so that's now reversing the definition. Remember, definitions go both ways.
Right.
If x is even,
So where did your extra set of parentheses come from?
so I'm overindulging in parentheses to keep my statements in parentheses. Because one more way I could have written this is if I say something like x is equal to the state. Maybe don't use x.
Well, isn't that so? You're just using the associative property.
Yes, from here to here, moving those parentheses over
Okay.
is using the associative property on or. We already know that or is associative. So x or y or z is the same thing as x or y or z.
Right.
Because remember, in Boolean algebra, a Boolean just represents a statement, either true or false. These are statements. X is in A, that's a statement. It's either true or false.
Right.
So everything that goes on from here down, well, you plug in your definitions, use Boolean algebra, reverse the definition, reverse the definition. So plug in definition once, plug in definition again, use Boolean algebra, plug in definition, plug in definition. And so I'm hoping when you go to prove these, what you're able to do that's not much of a struggle is going from this to this to this, and then from this to this,
Right.
and even to this. You should be able to do that. So just unraveling definitions both ways gets you almost exactly where you need to be. That gets you to here and here. And hopefully this one's a little bit more challenging for you. Get you to think this one might be a little tedious.
Yeah, I want to do that fast.
You're going to have to use the distributive property of logic. To do this one, you have to use the commutative property of logic. To do this one, you have to use the associative property of logic. To do this one, you have to do the distributive property of logic.
Wait, we're going to prove this in our homework, right?
Yes, you're going to prove this one and this one.
Oh.
And I prove the middle one.
So we don't need to prove middle?
No.
Wait, so we could prove the,
I proved
wait, are we
that
proving it right
union
now?
is associative. And you see how easy it would have been to do that intersection is associative. You literally don't need to change anything except for switch all those with intersection symbols and switch all our ors with ands. And it's the exact same thing for doing this.
Right.
Same thing's going to happen here, and not quite the same thing's going to happen there, but it's going to be close. Actually, it might be the exact same thing. Yeah, it should be. So once you prove one side of these, then you have the other side. So really, you have two proofs to do with that. Okay,
So if we need to prove it, we need to prove both union and the intersection.
I don't remember exactly what I asked you to do. I might have picked out so that you only have to do one. But just do whatever the homework asked you to do.
Okay.
So we just prove it by using the definition then, right?
You prove it by using the definitions directly, and then use the properties that we already know for logic, for or and and.
Oh, yeah, I know.
Good? Okay. Because there's a lot of similarities between set operations and just straight logic. Two go hand in hand. Okay, so now let's prove a pretty simple theorem about the size of A and B. So if A and B are finite sets, then the size of A plus the size of B is equal to the size of the intersection of the sets plus the size of, the size of the union of the sets plus the size of the intersection of the sets. And this will be really intuitive for you if you just look at the Venn diagram. So imagine I count everything in A, that counts everything in here, right? Plus everything in B counts everything in here, but then I count the middle part twice. You see that? If I count everything in A, and then I count everything in B, I count the middle part twice.
And you don't want to do that.
And you don't want to do that. So, the size of A plus the size of B, you're going to count everything that there is plus the middle part again. You're going to count all this plus the middle part again, and that's the same thing as counting everything in A and then adding it to everything you count in B. Another way that that statement is often reworked is to say that the size of A union B is equal to the size of A plus the size of B minus the size of the intersection. It's saying the exact same thing, we just reordered it.
Hang on, I don't understand. How does that equal that?
Okay, so let's look at this one, then we'll go back to that one. So I'm saying the size of A
I
union B
understand that one.
is this.
I understand that.
You understand exactly what I have written here?
Yeah.
So plus this to both sides.
For that?
Yeah, to get this.
Okay, but just explain that.
Well,
A plus B equals A.
the size of set A plus the size of set B is equal to the size of the union of the sets, which counts everything that's in here or here, plus the size of the intersection of the sets, which is everything that's in here and in here. Because this is going to count some elements twice, right?
Right.
Okay, but that's still doesn't make sense.
Here, let's make sense of this statement. I think this was more to it.
Hang on, look up there to the example.
Here?
Yeah.
Ah, okay, that's fine. How big is A?
I'm saying plus those two right there.
Yeah, so A is 3, or the size of A is 3, the size of B is 3. Right? The size of A union B is 5. The size of A intersection B is 1. 1 plus 5 equals 3 plus 3. That's exactly what that's saying. 3 plus 3 equals 1, or equals 5 plus 1. You see it? No questions? Alright, let's go over the proof. This is a counting proof, so it's going to be kind of worky. But it's going to be based in the fact that when you do A plus B like that, you count some elements either once or twice. Good? So let's go over it. Observe that the size of A counts all the elements in A, and the size of B counts all the elements in B, with the size of A plus B being the total count. So remember, we're saying this counts all the things in A plus all the things in B, and I'm going to show that this counts all the things in A plus all the things in B. Therefore, they count the same things. That's how counting proofs work. So now let's count the other way. Observe that counting all the objects in A added to the count of all the objects in B counts every element once or twice. Right? Once if it only shows up once, twice if it's in the intersection, which is what we're going to get to. Then A union B is the count of all the objects that show up at least once. Right? If it was in one or the other, then it shows up at least once. And A intersection B counts all the objects that show up twice. So then A union B plus A intersection B counts all the objects in A and counts all the objects in B. So we count all the ones that show up at least once, count up all the ones that show up twice, and we counted everything that's in A plus everything that's in B. Good? Might have been easier to do this proof instead. Probably should have done that. I think this is more intuitive way to think about it. Good? Anything feeling weird?
Will in a little while.
Huh?
So it will in a little while.
It will in a little while? Alright. Let's see an example of how we can quickly use this type of thinking now. So let's say I asked you, how many integers between 1 and 1,000 are divisible by 2 or 5? Right? might sound kind of like a hard question right out the door. How many integers between 1 and 1,000 are divisible by 2 or 5? That might seem a little bit tough, but let's get some sets real quick. Let's let A be the set of all integers between 1 and 1,000 that are divisible by 2. And let B be the set of all integers between 1 and 1,000 that are divisible by 5. So when we say how many integers between 1 and 1,000 are divisible by 2 or 5, we're asking how many integers are in A union B, right? In other words, we're wondering how big that is.
Yeah.
You follow the logic with me so far? That's what we're looking for? Okay. So yeah, we want to know the size of the set of all objects that are divisible by 2 or divisible by 5. So, what is the size of A? How many numbers between 1 and 1,000 are divisible by 2?
500.
500, half of them. And how many are divisible by 5?
200.
200, 1/5 of them. And how many are divisible by 2 and 5? Or in other words, how many are divisible by 10? 100, 1/10 of them. So we can quickly figure out with our intuition the size of A is 500, the size of B is 200, and the size of A intersect B is 100. And now we can figure out what the size of this thing is. The size of A union B is equal to the size of A plus the size of B minus the size of A intersect B, which gives you 600.
Oh.
So you can start asking questions that seem more complex by breaking them up into simple questions and using these operations. Good? Pretty cool.
Yeah.
Alright, more definitions. What does it mean for two sets to be disjoint? So sets A and B are disjoint provided their intersection is empty. They don't have any elements in common. They're disjoint. Good? And then we have another concept of pairwise disjoint. This is when we're talking about more than two sets. So if I have a bunch of sets, call them A1, A2, A3, all the way up to AN. If I have n sets here, I said they're pairwise disjoint, that's a P, if the intersection of any two sets is the empty set, as long as you're not talking about the same set. Pick two sets, make sure it's not the same set, so whatever I is and J is, wherever those subscripts are, make sure they're not the same thing. Then if their intersection is empty, we say those sets are pairwise disjoint. So now you have a notion of two sets are disjoint, and then you have a notion of you have a big collection of pairwise disjoint sets. Pick any two sets, their intersection is empty, as long as you didn't pick the same set twice.
Okay, no, wait, what? What's the difference between pairwise disjoint and just plain disjoint?
Disjoint is about two sets.
Two single sets.
Yeah, so disjoint only applies to two sets. Two sets are disjoint if their intersection is empty. A collection of sets, n of them, is pairwise disjoint if for any two sets you pick out of there that aren't the same set, then their intersection is empty. Because if you pick the same set twice, then the intersection of A1 with A1 is just A1.
That doesn't make sense,
It doesn't?
no.
Let's write one up here real quick. These are pairwise disjoint.
Okay,
Pick
I get
any
that,
two
I get
sets.
that, I get that, right.
But just don't pick the same set twice.
Okay, so. they're
So
not-
don't intersect this with this, because then you'll get 1, 2, and that's not empty. Make sure you pick two sets that aren't the same set. Their intersection is empty. But if I were to come along here and add 1, 7, now it's not pairwise disjoint. Even though
Now,
this,
all of those are not.
yeah, now I cannot call the collection of sets pairwise disjoint, because this intersected with this is not empty. So any two sets intersected, or any set intersected with any other set
You
has to
can
be empty.
literally pick those two.
Right. It's not that you can't find any. It's that no matter which two you pick, it will always be
Oh,
empty.
Okay,
Does that make sense?
yeah.
Okay. Pairwise disjoint. And now, quick proof. If A and B are disjoint sets, A union B is equal to the size of A plus the size of B.
Right.
In other words,
Makes sense.
Venn diagram, yeah, this should make obvious sense. If A and B are disjoint, means that A and B don't have anything in common. Then the size of A union B is the size of A plus the size of B. Makes intuitive sense, but let's do the proof using what we already have. we already have a theorem that the size of A plus the size of B is equal to the size of A union B plus A intersect B, right? That's this theorem. Now, since they're disjoint, we know that A intersect B is the empty set. That's what it means for A and B to be disjoint. And the size of the empty set is 0, which gets us there. Pretty straightforward?
Wait a minute. No.
So from
Where do you go from the
here
first?
to here
Yeah, that to the next one.
is using that theorem right there. From here to here is using the fact that A and B are disjoint.
Hang on. A plus B equals.
What is A intersect B?
What?
If A and B are disjoint, what is A intersect B?
Nothing.
The empty set, not nothing.
Right. That's what I mean.
So that's what we're doing. We're going from here to here.
Okay, but how do you go from the first one to the second one? Oh my god.
From here to here,
Yeah.
that's the theorem. We prove that the size of A plus the size of B is equal to this.
Oh, accounting. Right, okay.
So that's our first line. That's this,
Okay.
right? And then we know that A intersect B is the empty set.
Mhm.
And then we know that the size of the empty set is 0.
Right, okay.
And then we know anything plus 0 is just that thing. Good?
Yes.
All right. More definitions. We have the definition of a difference and a symmetric difference. So A minus B is equal to the set of all the elements in A that are not in B. So take everything in A and then get rid of all the ones that are also in B. That's what A minus B is. Make sense? And then the symmetric difference is, let's make intuitive sense of it first and then we'll go over what that says. The symmetric difference of A and B is everything that's in A or in B, but not in both.
Oh.
It's in A or in B, but not in both. So it is equal to everything that's in A or in B, minus the things that are in both. So looking at this picture,
So messed up.
the symmetric
So
difference
it would
of
be
this
three,
is
right?
everything over here and everything over here. Everything that's not green on this.
So it'd be 3. 3 would be subtracted? Oh, so it'd be 1, 2, 4, 5?
Oh yes, so for these ones it would be 1, 2, 4, 5.
Okay.
Everything that's in A or B, but not both, is a symmetric difference. Alright, what's A minus B up here?
A minus B up here.
Yeah.
What did I just say? Oh, A minus B. Oh, A minus. Oh, okay, right. 1, 2.
1, 2, perfect.
Okay.
Think you got it? Alright. And then De Morgan's law, I think this is another homework problem. And you'll notice that we also came across the De Morgan's when we did Boolean algebra. And I showed the counterpart to it down here. But let A, B, and C be sets, then A minus B union C is equal to A minus B A minus everything in B or C is everything that's in A minus B and A minus C. Oh, yeah. You trying to play catch up?
No. I'm paying attention.
You're caught up?
Yes.
Okay. So we have 3 sets. Then A minus B union C is equal to A minus B intersect A minus C. So everything that's in A that's not in B or C is equal to everything that's in A but not in B, and everything that's in A but not in C. You got that?
It's gross, but yeah, I got it.
I get why you feel that way. And then similarly here, everything that's in A but not in B and C is everything that is in A but not B, or in A but not C. And you're gonna, if you were to prove this, you'd use De Morgan's in logic once again. What's De Morgan's in logic? Not X or Y is the same thing as not X and not Y.
Wait, not?
Yeah,
A
going back to
minus-
logic.
A minus is not?
A minus is not.
Did I miss something?
Well, these are two completely separate things. Like the author doesn't even mention this thing that I wrote under here.
I know.
I'm just drawing a comparison for you.
Why am I having such a hard time with the minus? That doesn't look right to me.
Everything in A that's not in B.
So basically, you get rid of B.
Start
and
with
the
A,
intersection.
get rid of everything that's in B.
Why is that so weird to me? So how do you do it up there? And how can you freaking turn the union into an intersection?
Well, it has to do with the same way that the not distributes. So not X or Y is the same thing as not X and not Y.
Okay.
That's the logic that backs this type of thinking. And same with this. Not X and Y means not X or not Y. That's the thinking that backs this.
Not X and Y equals not X or not Y?
Yeah. So let's see. Let's say X is holding a marker and Y is holding an iPad.
Okay.
If Donnie's not holding a marker and an iPad, then either he's not holding a marker or he's not holding an iPad. So set up a scenario where it's true. Holding a marker and holding an iPad. Donnie's not holding a marker and an iPad. Is that true?
True.
It's true. Now let's look at this one. Donnie's not holding a marker or Donnie's not holding an iPad. Is that true?
Yes.
Tony's not holding a marker or he's not holding a marker.
Let's do a truth table.
He's not holding a marker or he's.
It's good. It gets messy when you try to logic through it. It means you're trying to think about it if you have questions.
Yeah.
So let's do just the left one, but I'm guessing it doesn't matter to you which of the two you do.
Well, no. Let's do the right one.
Or the right one. Did I say left? It's because I write the left side of the equation next to it. Okay, so let's go over all the possibilities. Possibilities are true, true, false, false, true, false, true, false. Right? Okay, so let's look at this one. And we'll set each scenario. Donnie's holding a marker, Donnie's holding an iPad. Donnie's holding a marker and an iPad is false. Or let's say Donnie's not holding a marker and an iPad.
That's false. 'Cause you are.
That's false, because I am. Wonderful. That's false. Okay. And then in this case, X and Y is so look at this case.
Hang on.
True and false is
So
false.
It's true.
So it's true.
Okay, but this
True.
is dumb. I know how to logic, like.
Okay, go back to the
science.
English.
Like you got me right on
Oh,
this.
actually, let's not do that. Let's do it one line at a time, and then I think you'll see it better that way. So, reset the scenario. Donnie's holding a marker, Donnie's holding an iPad. Donnie's not holding a marker and an iPad was false, right? Donnie's not holding a marker, or Donnie's not holding an iPad.
Holding false was false.
I just do
Donnie's not holding a
see
marker.
how that works.
True or false?
Donnie's not holding a marker. False.
Donnie's not holding an iPad.
False.
Donnie's not holding a marker, or Donnie's not holding an iPad.
False. Yeah, I get how that works. Great. But also, like, how are they the same thing?
I know. I think as we do it line by line, it's going to click in your head. I think that these ones are going to be more useful to you.
Okay.
So, now let's set the case, put the iPad down. Donnie's not holding a marker and an iPad.
True.
Oh, true.
True. Am I holding a marker and an iPad? No. True. Donnie's not holding a marker, or Donnie's not holding an iPad.
True.
True. Is it starting to click?
Yeah.
There you go.
Okay.
Let's do this one. Donnie's not holding a marker and an iPad.
True.
True.
Huh.
Donnie's not holding a marker, or Donnie's not holding an iPad.
True.
True.
I see.
Your intuition made the leap?
Yes.
All right. Wonderful.
Okay. Great.
That's good. Logic's can get you stuck over and over again.
Yep.
Okay. So that's De Morgan's. Chances are this isn't going to appeal to your intuition. Chances are you're not going to be able to just call that up from memory as time goes on. I don't have any hints or tricks except for to think about it this way. And then I don't know how to make this make intuitive sense except for just keep thinking about it. Okay. One more definition. And this is a very important definition, so make sure you're paying attention because this is never going to go away. And it's called the Cartesian product of two sets. So if you have two sets, their Cartesian product is a set of ordered pairs, x, y, where the left-hand element comes from A and the right-hand element comes from B. So it's a set of all ordered pairs you can make where the left-hand element comes from A and the right-hand element comes from B. So let's see an example and then we'll cover the definition again. So if I have A cross B, the cross product of A and B, where A is 1, 2, 3 and B is 4, 5, 6, then that is a set of all ordered pairs I can make where the first element comes from A, 1, 2, 3,
Right, that makes
and the
sense.
second element comes from B, 4, 5, 6. So 1, 4, 1, 5, 1, 6, 2, 4, 2, 5, 2, 6, 3, 4, 2, 5, 2, 6. So all the possible ordered pairs I can make where the left-hand element is 1, 2, or 3, and the right-hand element is 4, 5, or 6. Now, let's flip them, because it's not the same. B cross A is not the same thing as A cross B.
Right.
B cross A is a set of all ordered pairs where the left-hand element comes from B and the right-hand element comes from A. Note they have the same size, but they're different.
Not the same elements.
Not the same elements. And then, one more thing to know is that the size of the cross product of a set is equal to the size of A times the size of B.
Oh.
And you'll notice this should make perfect sense with our rule of multiplication for lists. You're counting all the lists you can make where the first element comes from A and the second element comes from B. Which is exactly n times m from our previous class when we did that. Counting lists. Does that make sense?
Yes.
So this one should make pretty good intuitive sense. And that is the end of set operations. So the next section, we just do 2 proofs, and then we're done with new material for today. So
Erase.
don't erase.
Well, I mean, you can erase this. That's all.
You need all that.
Yeah, I want to write about that.
You have it all on the
I don't
lectures.
look. I don't go and look at them. I just write it all down.
Well, maybe now you will. I could probably do the next proof in just a second. Yes, I. So Levi's falling asleep, so we'll take a break.
I'm trying, man. I'm really trying.
It's all good. Sometimes guys go to sleep.
I didn't get as much sleep as I needed last night, so.
So take a break, come back, we'll do 2 proofs, and then you can do homework. Or you can sleep more. your algebra test today.
Oh, you have that for me, right?
Yeah, I know how I'm gonna do it. I'm just gonna have you use the book
Okay.
because a palette book works. It's actually real easy to do.
Okay. And then you're just gonna give me some problems with it?
Yep.
Okay.
So
Yeah, all good.
can do that whenever.
Who was your class last year?
Oh geez, not good with names. Let's see. I have Taylor Horsley, Megan Timpson, Miranda Colley, my sister Miriam.
Miranda?
Is that her name?
Why was Miranda in here? I know she was, because she told me, but why?
I don't understand the question.
That makes me wonder.
Why not?
Well, that's funny, because it's well, I mean, she was always in advanced math, so why was she doing math in senior year?
Oh, I'm sure she's doing it just because she wanted to. Who else do I have? I have Jeremy Dockstader, Roberta Timpson, my brother James.
Did you do calculus last year?
No.
So this is your first year teaching it?
Yes.
Cool.
Last year I did discrete math and trig, which was miserable.
Yeah. You're not teaching trig this year?
No, I'm never doing that again.
That's so sad, why? I mean, like, I understand that we were pains in the butt, but like.
It's not that you're pains in the butt, it's that,
Nobody tried it, well.
no, I have students that tried. It's that half my class didn't belong in the class to begin with, meaning they were going to fail and there was nothing I could do about it. And so they were just a burden to the rest of the class to be in there that whole time. And then I was ill prepared for the class as well. I didn't know I was doing it until an hour before I started teaching.
Really?
Yeah.
Oh, yeah, I think
So I didn't have the time to find textbooks I wanted, so I just used a textbook that was already being used, which I don't like. It's a rush of material because it's really a combination of college algebra and trig, and it's targeted at application rather than teaching you the material. So I happily do a trig class that was actually just trig, and I'd happily do a college algebra class that was just college algebra. Except I wanted to do a trig class, to a class that I didn't teach geometry to. Because I want to give them the prereq material.
Are you going to teach geometry again this summer?
I don't know. I'm really tempted to do an algebra course because, holy cow.
Algebra what?
Algebra.
Just algebra?
Algebra made sense until it got.
We would use a college algebra textbook, but we would do algebra. We would start with, what's a real number?
That would be so useful because
That would be
going through
helpful.
algebra, you don't do that. It's like it makes sense until a point, and then they start giving you facts, kind of, and you kind of just have to memorize it. You don't know why it works, but you just do it.
Right. And
I don't even know what a freaking real number and a whole number and a natural number.
right, if I were to ask you for the axioms on real numbers, probably 2 kids in the school would understand my question, let alone know how to go about answering it. And so,
Which is so strange to me.
yeah, there's been a push in education
Yeah, I don't want to freaking graduate high school with not the information that I have, without the information.
I'm gonna like get through college algebra, have taken the course, be able to do it and not understand almost any of it.
Yeah, exactly.
Yeah, there's been this big push in education to make, particularly for mathematics reform, to try and make math classes more hands-on and more about analyzing data than about learning math.
Yeah.
And you guys have absolutely witnessed the consequences of what that is. And it's getting worse and worse and worse. And so the product of that is more and more kids are learning, more and more the education of your math is focusing on scenarios to apply the math to, rather than the math itself.
Yep.
And also, what's happening is because they're not going into depth in the math, you're getting more breadth of math. And so you're exposed to all this math, but you have no fundamental understanding of any of that math.
Yeah.
And
It's
so
like you know how to solve it, but you don't know why it works.
they did, listening to a podcast, one of the guys, they did a survey of college professors, what they want out of math students. They said, I want 3 things. I want them to be able to know how to do basic algebra. Meaning, they know how to add, multiply, subtract, and distribute. Number 2, they know how to work with ratios. Number 3, they know how to work with basic linear equations.
Not even the reading.
Huh?
Not even exponential and non-linear equations.
Nothing else. Math professors are saying if students were coming into college with just that understanding, I can take them from there and get them to where they need to be. But they are not coming in with that understanding. It's absolutely dreadful.
Now, why do I feel like high school doesn't freaking teach you what you need to know?
The problem with high school is that
It's like the worst.
you have a choice. So here I have my students coming into school, and now I have to make a choice. I have to either continue with the system that they're already in,
Right.
which sucks,
Mm-hmm.
or I have to start from ground zero. And those are my 2 options.
Right.
What do? Do you start from ground zero? Do you say,
Just start where they're at on your page, and I can be on your page.
well, and then the other problem is that we group so much students by age as opposed to what classes they should be in, that when I'm addressing a class, not this class, but when it was my trig class, I can't get on their level because they're not on a level.
Right.
I've got students up here who are bored by the time I am talking for 5 minutes, and students that I could talk to them for 20 hours and I still couldn't explain the material to them. And so when you have such drastic extremes because you're all lumped together because you're the same age,
Right.
then getting on your level just isn't an option.
That's why I like small classes. Because
Yeah.
You can get on our level with someone.
Small classes are easier. You can make sure students are keeping up. But also, in general, if you have a small class, if you have not a core class, the people who are in the class are there because they chose to be there, not because they're required to be there. And when you're dealing with kids who are only in your class because they're required to be there,
Right.
it's exhausting. But I can't believe what's happening, and I can't believe where it's coming from. I found out where it's coming from. And it's coming from economists. People who have economics degrees are pushing reform in mathematics. Now, you guys don't have a lot of economics experience, but it's a social science. You know what I mean by social science?
Yeah.
I mean, it's a social science. What's it sure of? Nothing. That's what it's sure of. Absolutely nothing. And it's trying to dictate the way that mathematics should be taught, and it baffles me. Because I was listening to this guy explaining it, and it all sounds good to an ignorant ear. Like, let's focus more on what they're actually going to be using out in the real world as opposed to stuff that they never use. So one of the surveys that they did, They were surveying people who had left high school, and one of the questions was, how often have you used geometry since you left high school? And like, or would you say that you used geometry on a daily basis since you got out of high school? And 2% of people said yes, or less than 2%, something like that. And so the argument that this economist is putting forward
You're
is,
saying get rid of it?
yeah, it's saying, why are we teaching geometry in high school when you don't go out in the real world and use geometry?
Geometry teaches you how
Let's
to paint.
yeah. People who understand geometry understand the stupidity of the statement. But why don't you replace it with some data analysis type class and then do that instead? And so they were bragging about these classes where the students go pick something that they're interested in, like the correlation, I think one of the examples was between height and weight of people. So they went and they spent the year collecting a bunch of data about the height of people, the weight of people, and then they go and they do some graphing and like, there's a good class that gives them a lot of good hands-on experience. It's like the math that they learned in that whole thing, I can teach a student in a day, no problem. So you've wasted tons of time. You haven't taught them any of the other math. And then yeah, like you said with geometry, most people have lost sight of the fact that the reason that you study geometry is to learn how to logic and deductive reason.
Right.
Geometry is just a medium that you use. Because there's no system in mathematics that starts on easier postulates to understand than geometry. Anyone can understand Euclid's postulates, and I can make those make sense to it. If I go start with the axioms on the real numbers and start trying to prove things with those, I'm going to lose the majority of my audience real quick. They need to discipline their mind in something that's easier to follow, something that's more visual, less abstract, which is why geometry is so great, because it's easy.
I feel that. I'm like, yeah.
Yeah.
It's
So,
like it broadens your mind in a way, like kind of subtly, that you can like think about the things.
well,
that
at
don't
the
even
very
pertain to this.
least, you should have drastically improved your ability to deductively reason. Because it's like that geometry textbook I was using. I could go take high school graduates, I could read them the sentences at the start of that book and say, what is this statement logically saying? And the majority of them would fail if I gave them a point for each one that they did it, saying getting 60% of them right means you understand it. They can't understand basic statements.
Right.
They don't know what that statement is actually saying, the logic of that statement. It's baffling. I mean, you think about
understand that because
how much
it's
you
very
struggle with
hard.
just an implication. You remember going over implications in this class?
Huh?
Implications, logical implication.
Oh yeah, yeah. This is what
X implies Y.
Yeah.
That is such a basic logical operation applied to so many statements. It's crazy. If this is true, then this is true is a logical implication.
Right.
And the amount of people who can understand the logical implication, just like that, it's surprisingly low.
Makes me
So,
mad.
yeah, it's completely frustrating because what do you do about it? So you guys have your crappy geometry that you had, which is terrible. I feel bad for Sophie having to teach out that book.
I had good.
Yeah, you did, but they didn't.
Well, I
You
don't-
did it for the college, right?
Yeah.
Yeah, and she used a textbook that I used over the summer, which
Oh,
is a phenomenal
Is it
textbook.
that little red one?
Yeah.
Yeah. Did you use that?
No.
Oh.
I just know that all my siblings have used
You
that.
guys did it online. You should take it from somebody.
I would love to. I didn't know you were teaching it last time.
Yeah, I didn't know that the
You
amount
were
of
teaching
interest
it.
was going to be in it. Yeah, it kind of turned into my trig class. Some of my students requested I do a class over the summer. And then because I knew what Masada was doing with geometry, I said, okay, I'll do that. And then the majority of my students weren't even trig students that I had. Like 4 of my students were junior high students.
That's awesome, honestly.
Yeah, it is awesome.
They're all your siblings, so.
Yep, all my siblings. Because I can get them to keep going.
Us Simpsons.
I just show up to dad's and I'm just like, let's go. And then they feel pressured to do it. And I feel bad because Laura actually wanted to do this class. I didn't realize that.
She did?
Yeah, and they wouldn't let her.
Why not?
This is a junior level class.
Oh, this class?
This class,
Oh.
yeah. So I would have let her be in it, but I didn't know she was trying to get in it.
Just because it's junior level, that's it? Or,
It's junior level. She hasn't taken Algebra 2.
and that's important for this class? Will we be
Oh,
getting?
yeah.
I would have let her in the class,
It's.
but as a general rule,
I mean, we haven't gone past algebra 1 so far.
yeah, what's a prereq to a class? It's kind of a weird thing to come up with because while the actual math involved in this class is light, the logic involved in the class is heavy.
Right.
So it drastically helps. I mean, it helps more if you've done a geometry course than if you've done an Algebra 2 course.
Right.
Even though there's more algebra things going on in this class. And she did geometry with me, so I feel confident in her competency. Anyways, moving on, counting proof. So we're gonna do 2 quick counting proofs. Are you still writing all that?
I'm done with this, just writing this board now.
Okay. Finish writing your notes. Feel free to work on homework for a bit, and then when you're ready for me to continue, we'll continue.
Here, I'll just focus.
Well, I don't know how much of this I'm gonna need.
Is it a
You're
really
gonna
big
need this
group?
whole board?
I have 2 proofs to do,
Oh.
so, and they're not even small.
Okay.
So, I'll take time to fill these out, write it out. You can start working on your homework, and then we'll go over the proofs. Jeez. You done with the right hand side of the left board?
Yes.
Okay. still got some work to do on the second proof, but we'll go over the first proof first. Okay, so we need to do a counting proof that 2 to the 0 plus 2 to the 1 all the way up to 2 to the n minus 1 is equal to 2 to the n minus 1. You understand what we're trying to prove? Do we need to see an example real quick? So let's say that n is, pick a number. 3. So we need to show that 2 to the 0 plus 2 to the 1 plus 2 to the 2, all the way up to n minus 1, 3 minus 1 is 2, is equal to 2 to the 3 minus 1. What's 2 to the 0? 2 to the 2, or 2 to the 1? 2 to the 2? For a total of?
8.
Almost. 4 plus 2 plus 1 is 7. 2 to the 3 is?
8.
Minus 1 is? 7. So we're saying pick any n, and this will always hold. You understand what we're trying to prove? It is cool. And you'll prove this again later on in the course, except for using proof by induction. But for now, we'll use a counting proof. Okay. So first off, if we're going to use a counting proof, the question we need to ask is, what does it count? So what does 2 to the n count? It counts all the possible subsets we can make out of an n-element list.
It's a power set, basically.
Yeah, it counts a power set. Remember, if A equals a set 1, 2, 3, how many subsets of A can I make?
8.
I can make 2 to the size of A, which is equal to 2 to the 3, which is equal to 8. Remember that? Okay, so 2 to the n counts the number of possible subsets I can get from an n-element list.
No.
Or n-element set, sorry, not list, set. So we're counting subsets. Good? Now notice we have 2 to the n minus 1. So we're counting all the subsets except for 1. What would be a natural subset to ignore?
Yeah, set.
The empty set. So your typical suspects are either going to be the empty set or the set itself. In this case, the empty set's the right answer, or at least the answer I used. So notice that 2 to the n counts all the subsets of the set 1, 2, all the way up to n, except the empty set. Does that make sense? Good? Alright. So observe that 2 to the n is the number of subsets that can be created from the set 1, 2, all the way up to n. Then 2 to the n minus 1 is all the subsets except the empty set. Okay? So now I need to show that this is all the subsets except the empty set. And then I'm done, right? They count the same thing, therefore we're done. And obviously the left-hand side is the hard part of the proof.
Yeah.
So, left-hand side. And I'm going to use this table to help it appeal to your intuition. So observe that 2 to the k minus 1 counts the number of subsets with k as a max element. Now I know that was dense, so let's look at the chart and then I'll read that to you again. So we're going to write down all the subsets that we can make that have this as its max element. How many subsets can I make that has 1 as a max element?
1.
Just a set containing 1. Right? There's no other subset I can make of this set, 1 through n, that has 1 as a max element.
1 meaning like the greatest?
Yeah, greatest element, the biggest number in there.
Okay.
Element as in number or element?
Element as in it's a number inside this set.
Okay, but hang on. So if the max was 2.
So if we say 2,
Listen. If the max was 2, then it would be 2 because you can go 1, 2, and you can't go further, or is it 2?
right, if I stick 3 in there, 2 is not the max element anymore. 3 is, right? So do you see how this is all the subsets with only 1 element? This is all subsets with only 2 elements. This is all the subsets with only 3 elements. What did I say? I don't even know what I just said. This is all the subsets with 1 as a max element.
There we go.
These are all the subsets with 2 as a max element. And these are all the subsets with 3 as a max element.
I know what you meant.
Okay, well, should assume, I guess. So, in general,
Oh, that makes sense.
yeah, so here's what our count is, but in general, here's how we can view it. If I want n to be the max element, I have to have n in there, right? And then there's n minus 1 options for these ones. N minus 1 numbers I can plug in there. And I choose, do I include it, yes or no? So I have two options. Do I include 1, yes or no? Do I include 2, yes or no? Do I include 3, yes or no? All the way up to n minus 1. Do I include n minus 1, yes or no? So I have two options n minus 1 times. Right? Is this just obvious and I'm just pounding it hard?
Well, no, I mean, it makes sense. It just.
So looking at this one, we had to have 3. Then we can choose, do we want to include 2? Yes or no? Do we want to include 1? Yes or no? So two options gives us a total of 4. So do you see how I get my 2 to the 0, 2 to the 1, 2 to the 2, 2 to the n minus 1? And maybe I should have put a generic k in the middle of here. So dot 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 k, some number k, I'm saying is 2 to the k minus 1. Why? Because in our list, we choose, do we want to include 1, do we want to include 2, do we want to include 3? Do we want to include k minus 1, do we want to include k? We have to include k, so that one's not an option. Right?
Right.
So 2 options for 1, 2 options for 2, 2 options for 3, all the way up to 2 options for k minus 1. Does that make sense? Yeah? No? Kinda? Say it again?
Mostly.
Mostly.
You're just using k as just a random number, right?
Yeah, it's some number between 1 and n. So I'm saying in general you can always use this formula. So if I were to give you a homework problem, and I say, how many subsets can I make of the set 1, 2, 3, 4, 5 with 5 as the max element? In other words, you have to include 5, right?
Right.
So then you would say, I can choose whether or not to include 1, that's 2 options. I can choose whether or not to include 2, that's 2 options. I can choose whether or not to include 3, that's 2 options. And I can choose whether or not to include 4, that's 2 options. So 2 times 2 times 2 times 2, 2 to the 4. So if 5 is your max element, you have 2 to the 4 options. If k is your max element, you have 2 to the k minus 1 options. Does that help?
Mm-hmm.
Think you got it?
Yeah.
Okay, so let me read the sign of the proof one more time. Observe that 2 to the k minus 1 counts the number of subsets with k as a max element. That sentence now makes sense?
Yeah.
Okay. In other words, and maybe I don't need this now that I figured I was going to need a picture on the side to explain it. In other words, counting all the sets of the form, some elements all the way up to k, where all the elements are less than k is 2 to the k minus 1. Maybe that just made it worse, maybe it didn't.
Probably. That makes sense.
Okay, so continuing. Then counting all the sets with 1 as a max element is 2 to the 0. With 2 as a max element is 2 to the 1, as I showed there. With n as a max element is 2 to the n minus 1. Right? So then you add them up. I count all the sets with 1 as a max element plus all the sets with 2 as a max element plus all the sets with 3 as a max element plus all the sets with 4 as a max element plus all the sets with n as a max element is this. And now we counted all of the sets except for the empty set.
What's that
It's
block
a lot
up
more
there?
simple than I thought it was going to be.
What's what?
Is that like square?
At the end.
At the end?
What did you say, Stan?
That's what you put at the end of proofs. So you used to put QED at the end of proofs, which was shorthand for a Latin phrase which meant, and thus it is demonstrated. But now it's convention, you just put a little filled-in box.
Okay.
Or sometimes it's an empty box, but just a box demonstrating that the proof is done. Instead of some 3 letters which represent some Latin phrase that no one knew.
Okay.
So, that's my box. Okay, that proof makes sense?
Yes.
Pretty sure that was on your test, so.
What?
Yeah, I'm a jerk like that.
It's on our test or it was on our test?
I'm pretty sure it's on your test.
So we.
Pretty sure it's on the test I'm giving you next week.
Okay, no, it doesn't make sense.
See, that's what you say to see if it really makes sense.
Like, it makes sense in my head, but I'm not sure I can reprove it.
I don't understand
The
what
proof's
you're
in the
trying
book
to prove.
as well. The author proof. Huh?
I don't understand what you're trying to prove.
I'm trying to prove that this is equal to this.
Oh.
And I'm saying this counts all the subsets of this set, except the empty set. And this counts all the subsets of this set, except for the empty set.
Okay.
So this counts all the subsets with 1 as a max element. This counts all the subsets with 2 as a max element. This counts all the subsets with 3 as a max element. This counts all the subsets with n as a max element.
Right. Not counting the empty set.
So if you don't count the empty set, it's going to have a max element. That max element's either going to be 1 or n. So we counted all the possible subsets, except the empty set. So this counts all the subsets except the empty set. This counts all the subsets except the empty set. So they count the same thing, therefore they're the same number. That's how counting proof works.
2n minus 1, is that the same as this right now? 2n minus 1?
Yeah, that's my point. 2n minus 1. That 2n minus 1.
That one. The other one. Yeah.
Oh, that is not the same as that. This is 2 to the n minus 1.
Right, so how do you do that and count all of it?
How does this count all of it? 2 to the n counts all the subsets. Minus 1 gets rid of the empty set.
How does 2 to the n count all the subsets?
How many subsets of A are there?
Hang on.
2 to the size of A, 2 to the 3, or 2 to the n.
Okay, so let's say n equals what? Is it any number?
Any number.
That makes sense, okay.
Well, any natural number. Okay. So, good luck with that one.
Yeah.
This next one is not on your test, so don't worry about it. You can just start working on homework or something. Alright, next proof. Which I'm not done with yet. We're proving that 1 times 1 factorial plus 2 times 2 factorial plus 3 times 3 factorial plus n times n factorial is equal to n plus 1 factorial minus 1.
We did this one already.
You didn't do this. You made a conjecture.
Oh, we didn't prove it.
You didn't prove it. There's a reason that they didn't ask you to prove it, because it's kind of messy. So now let's count it. Rather than going through this, let's just get our logic around it first. So what does n factorial count in general? What does k factorial count? What is k factorial count?
K minus 1, dot, dot, dot.
Well, that's equal to k times k minus 1 times k minus 2, right? So in other words, let's be more concrete. What does 5 factorial count? You know it's equal to 5 times 4 times 3 times 2 times 1.
Oh, so.
But what does it count? What's something that could possibly be the count?
It's like the number of lists or something.
Yeah.
Or something.
It's the number of ways that we can arrange 5 objects,
In a
is
list.
one way to think about it. A list is what you use mathematically to arrange objects because order matters and you can't have duplicates. So it's the number of 5 element lists we can make with the numbers 1 through 5. It's the number of ways I could order the numbers 1, 2, 3, 4, 5. Those are all logically equivalent. Am I losing you in any of that? Really quick, 3 factorial. To keep our things small. 3 factorial, you say, is
2 times 2 times 1.
3 times 2 times 1, but it counts all the 3 element lists I can make with the numbers 1, 2, 3.
Or
So I could have the list,
it's really just any list that you can make with 3 elements, right? Doesn't
right, but we're picking something that it counts. You just need to find something that it counts. So pick something convenient. So it counts 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 2, or 2, 3, 1, 3, 2, 1, and 3, 1, 2. These are all the 3 element lists that it counts. Because you have 3 options for that first element, you can do 1, 2, or 3. And then once you pick that first element, you have two options for the second element. You can do 2 or 3. And then once you pick your second element, you only have one option for your third element.
Right.
Right? So 3 factorial counts these lists. 5 factorial counts how many we would do with 5 lists, which is 120, so I'm not going to write them out. Good?
So 3 factorial equals 6?
Yeah. 3 times 2 times 1 is 6. 3 options for the first element, 1, 2, or 3. Then 2 options for the second element. And then 1 option for the last element. 3 times 2 times 1. So factorial is chosen so it counts the number of ways objects can be arranged. That's the idea it was meant to capture. Okay. So, what does n plus 1 factorial count?
N plus 1 factorial. Count.
It counts the number of lists I can make with the numbers 1 through n plus 1. Exactly. So I take those numbers, arrange them in a list. Arrange them in a list.
Right.
Take the numbers 1, 2, 3, all the way up to n plus 1, and arrange them in the list. How many ways can I do that? N plus 1 factorial ways. Right? In other words, imagine that we were creating one of these lists, and I had these options to pick from. How many options do I have for the first element in the list?
N plus 1?
Well,
N plus 1, right? I have n plus 1 options for this one. And then for this one, I have n options.
N.
For this one, I have n minus 1 options. For the last one, I have 1 option. For the second to last one, I have 2 options. And so it's that times that times that times that all the way down, which is equal to n plus 1 factorial. The number of lists, the number of arrangements I can make with these numbers. How many ways can I arrange those numbers? This many ways.
Cool.
Good?
Yes.
Now we've got a stupid minus 1. Well, shoot. Which one are we going to get rid of?
That doesn't make sense. Like, why don't they just stick with the N? 5 plus 1, 2.
So that the left-hand side has an n. You don't have to use an n minus 1 and an n, or an n and an n plus 1.
Okay. That's lame.
Huh?
Lame sauce.
Well, doesn't matter. But, am I losing you guys on this?
No,
No.
I'm just thinking.
So n plus 1 factorial. Okay, so now we got to get rid of one of those. What's the most obvious one to get rid of?
N plus 1. No, give me the empty set.
The empty set isn't one. All these lists have n plus 1 elements in them.
Huh?
And there's a crap ton. Like when I did all the lists with 3 elements in them. Right? So when we had 1, 2, 3, what were all our lists? We had the list 1, 2, 3, 1, 3, 2, 2, 3, 1, 2, 1, 3,
3, 2, 1.
3, 2,
3,
1, 2. So now we need to eliminate which one of those. What's the most obvious one of those? Because we got a minus 1 here. We need to say what could this number be counting?
Okay.
What could that number be counting? That could be counting all of these minus 1. If n was 2, then n plus 1 is 3, right? So here's a case where n equals 2.
Right. Yeah. What's the one that's most obvious?
Yeah, if you had to get rid of one of those, which one would you get rid of?
3, 2, 1.
3, 2, 1. That's interesting. You chose that one.
2, 3, 1.
I'm going to get rid of 1, 2, 3.
Yeah. Yeah.
That's what I was going to say.
So that's what I'm going to say in my proof. I'm going to say that this counts all the ways that we can arrange n plus 1 objects where they're not in increasing order, where it's not 1, 2, 3, 4, 5, 6, all the way up to n plus 1. Okay?
Right.
Why do you need a list like that?
Why do I need a list like?
Well, I'm saying, I'm just trying to think like,
Yeah, you're confusing.
I'm wondering how did this conjecture come into existence? Like, what's the point of it?
What's the point of it?
No, I mean, I think I phrased that a little wrong. Let's try it again. I'm wondering, like, how did we come up with this equation?
You came up with it.
I know I did. I can't remember how.
Well, you played with it, you made a table, you looked at the numbers, saw if you could find a pattern, and you eventually found the pattern.
Right.
So now the question is, the author is intentionally doing this.
Oh, I guess that makes
We
sense.
introduced that problem to you. Here, you play with this, see if you can make a conjecture. You made a conjecture. The author comes back later and says, okay, now see if we can prove your conjecture.
Okay.
Okay? So, what I'm saying is this counts all the lists we can make with the objects 1 through n plus 1, except for the list where we put all the numbers in ascending order. 1, 2, 3,
So
4,
why?
5.
What's the reason that we want to get rid of that list specifically?
Well, we have to get rid of 1
Right. But why is
to
that
make
one?
this count because that's an easy one to work with. It might seem unintuitive that we get rid of the one that's easiest to work with, but we're going to have to work with the one that we're getting rid of a lot to make sure we don't get it. So because it's the nicest.
I guess I'll see what you mean as we go here, right?
You understand which one we're removing though, right?
Yeah.
1, 2, 3 is the one we got rid of. So here's another way that you can say, what is this counting? This is counting all the lists I can make with the numbers 1, 2, 3, where 1 doesn't come first, 2 doesn't come second, and 3 doesn't come third. Right? So maybe you want to count all the ways you can arrange objects where you don't want one specific ordering. That's what we're counting.
Oh, okay.
Okay? Alright. So observe that n plus 1 factorial counts the number of ways the elements 1, 2, 3, all the way up to n plus 1 can be arranged in a list. Good up to there?
Yeah.
You never went over B minus A.
B minus A.
Is that just the same thing? Just switch?
Yeah, it's the same.
Oh, yeah.
No?
The order,
This symmetry.
they're just variables. Right? X minus y and y minus x are the same thing. They're just variables. So you're actually just going straight to the homework. You took me serious.
Well, I don't want to freaking learn this. That hurts my brain.
That's the point. If you come to this class and your brain isn't hurting a little bit,
My brain is already so packed full from today that I can't learn anything else.
let's see if we can burst it.
Oh, you want to try?
Yes, that's exactly what I want to do.
Okay.
But I can't do that if you don't pay attention.
Yep.
All right. So n plus 1 factorial counts the number of ways we can arrange those elements in a list, right? Should be good at least up to there.
Okay.
Then n plus 1 factorial minus 1 it counts all the arrangements except for the arrangement 1, 2, 3, all the way to n plus 1. The one where they're all in order. Okay. So now we're going to count these kind of weird, and I'll make a side graph as we explain this. So maybe read this and then go to the side graph. So let k be some integer between 1 and n, and consider the list whose first k minus 1 elements are just the actual numbers that go there, but whose kth term is not k. So let's see what I'm saying there. So I'm saying let's count the list and let's do it like this. Here's what k is going to be. K is going to increment 1, 2, 3, 4, 5. And for the sake of keeping our picture finite, we'll say that n in this case is equal to, what should we say? 6. So we'll do k, 1, 2, 3, 4, all the way up to 6. Okay? So what I'm saying is, let k be an integer between 1 and n. In this specific example, 1 and 6.
Does that include n?
Yes, including n, and 1.
Okay.
So inclusive. Whose kth term is not k, but the elements up to k are just their associated numbers. So in this case, we're saying this element, its first or its kth term cannot be 1. This one, right smaller, can't be 1. We'll fill it out later. This one we go 1, but 2 can't be 2. This one we go 1, 2, but 3 can't be 3. Still ranks big. 1, 2, but 3 can't be 3, and then we'll finish it later. This one's 1, 2, 3, but that can't be 4. This one's 1, 2, 3, 4, but that can't be 5. And this one's 1, 2, 3, 4, 5, but that can't be 6. And we'll do the count here. Okay. So you see what these are each counting, what k is in each of these cases?
Yeah.
Okay, so then, how many options do I have for this element?
None.
I have 6. I haven't used anything yet.
Oh, you're saying out of all of those. Oh, okay.
Yeah, so I still have, and maybe I'll use green for the amount of options instead of the numbers in there. So I still have 6 options for this element, 5 options for this one, 4 options for this one, 3 options for this one, 2 options for this one, 1 option for this one, and that finishes the list, right?
Okay.
You see what I'm saying there?
Yes.
Except for I lied, we don't have 6 options for this one, we have 5 options for this one. Because 1 can't go there, 2 can't go there, 3 can't go there, 4 can't go there, 5 can't go there, 6 can't go there. Good? So, in total, we have 5 times 5 factorial ways that we can finish that. Let's do the next one. I think it will help sink it in. 2. So we say the second element can't be 2.
Oh,
So there's only 4 options here.
right.
And then there's 4 options, 3 options, 2 options, 1 option.
Wait, why is there 4, 4, 3?
Same reason there was 5, 5. So this was 6,
Oh, okay, we're good. I'm good.
but then we can't use 1,
Right, right,
which makes it a 5.
right.
This would have been 5, but then we can't use 2, which makes it a 4. And then this would be 4, but so let's write the number. So this is 4 times 4 factorial.
Okay.
Once again, we have 3 options here, 3 options here, 2 options here, 1 option. What did I do? Oh my god, my numbers aren't lining up. Let me make sure the numbers line up. Because I had extra comment. 2. So we have 3 options here, 3 options here, 2 options here, 1 option here, right?
Mm-hmm.
Similarly, we have 2 options, 2 options, 1 option. We have 1 option, 1 option, 0 options. You follow that? The associated numbers, this is 3 times 3 factorial, this is 2 times 2 factorial, this is 1 times 1 factorial, and this is 0. There's no ways to finish that.
Can I ask you a question on that?
No. So, when n was 6, then the number of ways that we could do this was the sum of these all the way up to 5. Right?
So it would be like,
This was all the ones that didn't have 1 in the first place. This was all the ones that had 1 in the first place but didn't have 2 in the second place. These were all the ones that had 1 and 2 in their places. Oh, I skipped one. That had 1 and 2 but didn't have 3 in its place. This one's all the ones that don't have 4 in its place, 5 in its place, 6 in its place. You see how we split it into those different cases that we counted?
okay.
So this is going to count all the ways that we can order those lists. We count all the ones that don't have 1 in its place, plus all the ones that have 1 in its place but don't have 2 in its place, plus all the ones that have 1 and 2 in their place but don't have 3 in its place, plus etc. And then that counts all the ones that don't have 1 in its place, and 2 in its place, and 3 in its place, and 4 in its place, and 5 in its place, and 6 in its place. You see how we broke it up case by case?
Yeah.
Okay, and that's exactly what we're going to say over here. So let k be an integer between 1 and n, and consider the list whose first k minus 1 elements are those numbers, k minus 1. So if k is 4, then whose first elements are 1, 2, and 3. Whose first k minus 1 elements are 1, 2, 3, all the way up to k minus 1. But whose kth term is not k.
Okay.
Then the kth term can be chosen in n plus 1 minus k ways. So let's make sure we understand that. So let's look at this when we were talking about this term. How many ways could I pick this number?
3.
I had gotten rid of k minus 1 of them. Right? Here's k minus 1 is 2. So I can't use those k minus 1 of them.
Okay.
And I also can't use the number 3 itself, so I can't use k of them.
So there's still 3 options though, aren't there?
Yeah, so there's n plus 1 options. Oh, sorry, n is 5, n plus 1 is 6. For this example, I think, right? Because we go up to n plus 1.
Alright.
So, if k is 3, then we can't use k of those options.
Is k just like the number it is in the sequence?
Or what?
It's both. It's the number and it can be its position in the sequence. K is, let's retrack what this is counting. When k is 1, we're saying all this list, I keep going to say sentence, all the lists that don't have 1 in the 1 position. When k is 2, we're saying all the lists that have 1 in its position but don't have 2 in its position. When k is 3, we're saying all the lists have 1 in its position, 2 in its position, but don't have 3 in its position.
All the way up to where?
All the way up to k. So the first k minus 1 elements are in their position, but k is not. So when k is 4, 1, 2, and 3 were in their position, but 4 wasn't.
Right.
So we have, for this spot, how many things can go there? We can't use 1, we can't use 2, we can't use 3, and we can't use 4, right?
You can use 5 and 6.
You can use 5 and 6.
Right.
So you can't use these k minus 1 terms, and you can't use the term that actually is. So you can't use k of the terms. So there's n plus 1 terms total, you can't use k of them. So when you're trying to pick what comes after k minus 1, you have n plus 1 minus k choices.
Oh, okay.
Okay. So that's kind of the big leap once you can see that. So the k term can be chosen in n plus 1 minus k ways. And then the remaining terms, all these remaining terms, can be chosen in n plus 1 minus k factorial ways. So there's going to be n plus 1 minus k remaining ways. When k is 4 here, after we put the first 4 in, then there's 2 remaining, or n plus 1 minus k.
Right.
So once we put in k items, there's n plus 1 minus k remaining. And those n plus 1 minus k terms can be used in whatever order we want. Right? So you have n plus 1 minus k ways of choosing this, and then n plus 1 minus k factorial ways of finishing it. For each one of those. So for each one of those, you have n plus 1 minus k ways of picking the kth element, times n plus 1 minus k factorial ways of finishing off the list.
Okay, so I think I lost sight of the overhead thing. Ways to do what?
To arrange the list, the elements in the list.
Okay. Okay.
So were you back to
Like, that makes sense.
Here's,
I'm just.
yeah, so how many ways can I pick this one? Is n plus 1 minus k.
Right.
I can't use the numbers 1, I can't use the numbers 2, and I can't use the numbers 3.
Mm-hmm.
So there's k numbers that I can't use to pick this element. So there's n plus 1 minus k ways I can pick this element.
Right.
And then to pick the remaining elements, it's just n plus 1 minus k factorial. So n plus 1 minus k times n plus 1 minus k
So
factorial.
it's just do the list.
So n plus 1 minus k is picking the kth term, and then n plus 1 minus k factorial is finishing
Right.
off the list.
Right.
Perfect. And then, I don't know if we need to finish writing out the proof, but I think that's the hard part. So now for the numbers k, 1 through n, it's going to give you this in reverse order. When I plug in 1, I get this. When I plug in 2, I get this. When I plug in n, I get this. For k.
Okay.
So that, do you understand what I mean?
I think I do. All the way up to k, so when you get to the kth term, you get the 1 times 1 factorial, right?
K is just some random number
Okay.
between 1 and n plus 1, right?
Why do you even, I mean, I see why we used k in proving it, but what does it actually represent?
It's just a general term. We're saying, I mean, k is incrementing through all these. I mean, okay, so let's finish it. So 6, then we could say something along the lines of n plus 1 minus minus 1 counts all the lists with 1 not in the first position. Oh, times 1 factorial. N plus 1 minus 2 times 2 factorial counts all the lists with 1 in the first position, but not 2 in the second. Right? Whatever this is, 7. Then n plus 1 minus 2, or minus k, times k factorial counts, as we've already said right here, so it counts all the lists whose first k minus 1 elements are 1, 2, 3, all the way up to k minus 1, but whose kth term is not k. Right?
Right.
That exact same thing you put in right here. Counts all the lists whose first n terms are 1 through n. Oh, that one doesn't work. Oh yeah, it does, because we go up to n plus 1. I keep mixing up what n is in my head. Whose first n minus 1 terms are 1 through n minus 1. I'm doing that backwards. Sorry. Sum again. It's supposed to be n plus 1 minus k times n plus 1 minus k factorial, not n factorial. Oops. I wrote all these wrong. But that's getting kind of verbose anyway, so maybe it's just faster to start. I mean, I almost kind of just want to write that this is the sum. Maybe say it this way. Then incrementing k from 1 to n gives, so k was a number, where did I first say k?
Step 3.
Step 3, let k be an integer between 1 and n. Okay, perfect. So we're going to increment k from 1 through n, doing this each time. So then incrementing k from 1 to n gives, plug in 1, we get
See, okay.
n times
That kind of makes more sense about what you were saying earlier. I didn't realize that.
okay, times n minus 1, n minus 1 factorial, plus plus, we'll eventually get to 2 times, oops, something I have omitted. 2 times 2 factorial plus 1 times 1 factorial, plus 0. Oh no, we don't get the 0 case because k never reaches n plus 1. It only reaches n. So that's it. So maybe that was a better way to say it. Here's what it is for the k term in general. Now increment k from 1 to n, summing it up as you go.
Okay.
And that gives you the sum, which is the sum.
So basically, you prove that n plus 1 factorial minus 1 equals your expression in step 5. And then you prove that the expression in step 5, when you increment k from 1 to n, gives you that sum.
I lost what you were saying in steps.
Okay, so what I'm saying is you prove, the way that you prove this kind of overall is you took n plus 1 factorial minus 1 and you proved that it was equal to that expression n plus 1 minus k times n plus 1 minus k factorial.
No. Okay. So I said, look, this counts all the lists except for the one that has each element in its position, meaning 1 in the first position, 2 in the second position, 3 in the third position.
Okay.
Okay? I said, here's a generic term that counts all the ones where k is not in its position, but all the elements before it are in its position. So this counts all the cases where 1's not in its position. This counts all the cases where 1's in its position, but 2 isn't.
2 isn't, right. And
This counts all the ones where 1 and 2 are, but 3 isn't. Where 1, 2, and 3 are, but 4 isn't. Where 1, 2, 3, and 4 are, but 5 isn't. And then ignore this one because there aren't any ways to finish with it. So that's 0. So here's where our k increments through. We do k goes from 1 to n, not n plus 1. Right?
Right.
So I'm saying if you count up all these lists, that's all the possible lists that we're talking about. This is a count of all the lists that never have 1 in its place, and 2 in its place, and 3 in its place, and 4 in its place, and all the way up. So summing up this is the same thing as this. They're counting the same thing. So let's think about a particular list that we're talking about.
Wait a minute. Wait, no, that's making sense. That makes sense. You're saying that in this case, doesn't, wait 1 second. Doesn't k
It starts at 1 and it ends at n.
Oh, okay.
Here, think about it this way. I ask you, how many lists can you make with the numbers 1 through 6 that don't start with 1?
Well, it'd be that don't start with 1, so
Uh-huh.
5 times 5 factorial.
5 times 5 factorial. Okay, and I say, all right, now that don't start with 1, or if they do start with 1, aren't immediately followed by 2. Okay, that don't start with 1, or if they start with 1, aren't immediately followed by 2, or if 1's immediately followed by 2, isn't immediately followed by 3, or if 1's immediately followed by 3, or, sorry, I'm screwing up my words, but I think you understand what I'm saying, right?
Yeah.
So we're counting all the possible cases where we didn't have 1 immediately followed by 2, immediately followed by 3, immediately followed by 4, immediately followed by 5, immediately followed by 6. That's the only case that we're not allowing.
Right.
There's only one case that we're not allowing.
And that's what we subtract.
Well, we subtracted it here.
Right.
Here we added up so we never got
Would be
it. I mean, so pick any list you want with the elements 1 through 6, and I'm saying one of these counted it unless you pick 1, 2, 3, 4, 5, 6.
right.
So pick, maybe doing an example might help. Pick some generic order.
Of what?
Pick some order of the numbers 1 through 6.
3, 5, 4, 6, 1, 2.
3, 5, 4, 6, 1, 2. That was counted right here. That is a list that doesn't start with 1. Now let's say you happen to pick 1, 2, 3, 4, 6, 5. That's really close. Well, that's the one case that's counted here. Etc. So this counted all the cases that didn't start with 1. This counted all the cases that started with 1 but were followed by 2. Etc., etc., etc.
Okay.
So when you add those up, you're going to end up with all the possible lists you could have made except for the actual list 1, 2, 3, 4, 5, 6.
Did you say footwear?
Counting proofs are difficult when you first come across them. They make your head hurt.
This is really a little confusing.
Good. Should be.
Like, I'm wondering if I'll ever get the hang of this. Is that?
Oh, you will. I remember when I first came across it, it was a nightmare.
I don't.
My gut feeling was you didn't really prove anything. You're just saying a lot of stuff. And maybe it's true, maybe it's not, and I'm having a hard time following you.
I am having a hard time following a lot of that. Like
Yeah.
It makes sense when you explain it, but even now, like, I'm not sure I completely understand.
It clicks and you go back and you look at it from the start and you're like,
That doesn't make sense anymore.
So yeah, that's a common phenomena with these types of proofs. The author has his own proofs where he tries to walk you through the intuition carefully. I mean, they're going to be the same generic outline, but he might have a different way of explaining it.
Are we going to be counting proofs anytime soon?
You've already done a counting proof.
When?
I don't remember, but you did one.
Okay.
But yeah, it's in a bit.
Oh, I remember. It was something like n to the n is equal to,
Can I use that?
yeah, n, what was it?
Okay, so yeah.
Was it n squared is equal to n, and n, I can't remember what it was. You did one now. There was on your homework.
Okay, then, yeah.
Because one of them counted all the 2 element lists you can make. I remember that.
Yeah. That's
Anyways.
so confusing.